quite a bit few, but hopefully this will be increased during the day. But the program is very tight, just as of yesterday. So let me call the first speaker of the morning session, who is Balázs, who will speak about the rotating universe, simulating rotating Newtonian universes, which is a pretty deep problem, because naively you think that everything is rotating, but all the calculations of the evolution of the universe today is supposed to be static and non-rotating, non-static but non-rotating. So this is an interesting point, how you can resolve this in a computational method. So Balázs, please.
Okay. So thank you, everyone. My name is Balázs. I'm a PhD student at the Eötvös Loránd University and at the Heavy Ion Group at Wigner Research Center. And I'm really glad that for this first presentation of the day, I can present you just a funny little project I'm involved in. And I am advised by several of my much more knowledgeable peers in the topic, who are all a part of the research group of the Cosmo Astro research group of István Csabai, who most of you might know well, who is it. And well, this topic is from the field of computational cosmology. And whether you're familiar with cosmology or not, please let me tell you some context about primarily about the current state of cosmology, the motivation of this specific research, and research in general in this field. So we usually say that cosmology is the study of the universe and its history as a whole. But essentially it does, or it aims to achieve two things. First is to, well, uncover and describe all the physical phenomena that affect the universe on the macroscopic scale. The second is to develop some kind of framework that can incorporate these physical phenomena in some unified manner. And this is why cosmologists usually refer these frameworks as standard models of cosmology or concordance cosmology or something like that. So basically what physicists does in every single field of physics as well. The main difference is in cosmology that this standard model currently is just the collection of assumptions about the universe, and all the physical models should adhere to these assumptions. Basically, and currently the most widely known or most widely accepted framework is the lambda CDM model with its own unique set of assumptions about the universe. This is basically the theoretical side of cosmology. The role of observational side of cosmology is to test and constrain both the models of these various physical phenomena in the universe and consequentially these unified assumptions about the universe as well at the same time. But what we saw in the past few decades is that more and more observational evidence is accumulating that is in conflict with the current framework, the lambda CDM model. Now, there is an even more growing disagreement on how to approach these conflicts. Some cosmologists argue that they can be ironed out in the confines of the lambda CDM model because they are due to statistical error or systematic errors in the observations, or maybe they can be tackled by introducing new physical phenomena that explains these discrepancies. But other people say that no, these problems are very real, and the lambda CDM model needs to be changed entirely or replaced entirely with a new one. But we all know you can't just push through new ideas through the scientific community. So despite all problems, the lambda CDM still holds very strong. And although the group of István Csabai already proposed or had a proposal for a new model in 2017, I think, I'm not sure about this one, which they call the Avera model. In this project, we went with the introducing a new physical phenomena option, namely a shear-free rigid body rotation of the universe, whatever that means. So the idea comes from a very simple observation that everything in the observable universe rotates. So from small particles to large astronomical objects, everything spins. So why not the universe itself? We have no idea, but anyway, we are curious of what would happen or what would we see, what would we observe if the universe would actually have some intrinsic rotation, again, whatever that means. So we expect that the rotation would introduce an anisotropic expansion of the universe, which means that the expansion rate of the universe would depend on the specific directions we're looking at. More specifically, it would depend on the axis of rotation. This is the theoretical prediction, and we wanted to test whether this effect is even observable or relevant, or yeah, that's the question. And we specifically wanted to answer this using cosmological simulations, because yeah, how else they're supposed to even investigate something like that. So far, no one has ever done this, and not the cosmological simulation part, of course, that exists for a very long time, but the simulation of a rotating universe. And there is a reason for that why no one has ever done this before. It is that our general approach to cosmological simulations is effectively unchanged since forever. It never really changed. Of course, there is a huge variety of cosmological simulations from the past 50 years, and they improved tremendously during that time. But the basic idea, simple idea behind them were always the same. So how do we even make a cosmological simulation? What does this all of them means? So we start from an initial condition, just like in every simulation. In this case, it represents some early state of the universe, where matter in the universe is distributed almost uniformly. And we evolved this system over some long time, which is basically the age of the universe. And then we measured the properties of this matter distribution at some later time, usually at the present time we are in right now. And then comes the basic idea I was talking about. I was mentioning for decades, cosmological simulations were always cubical and periodic. When someone wanted to simulate the universe, they always took a finite cubical region of the universe, filled it with particles, repeated this box indefinitely in every single direction, and then solved the relevant differential equations, which is the Newtonian gravity in case of cosmological simulations, to evolve the system in time. And this approach has both advantages and disadvantages, but what is relevant to us in this case is that we can't simulate a rotating universe with an infinite spatial extent in this with this method. So István Szabódi is the one who could tell you more about this, but a rotation would appear as a constant velocity flow in this type of setup, which is topologically actually just a 4D torus, but it won't have any acceleration like a rotating universe, or basically rotating anything should have. Great, we can't use the only method that everyone has used in the past 50 years, minor inconvenience. But fortunately, there is another way to make cosmological simulations, and that is exactly what was done for the first time by, again, the group of István Csabai in 2018, when they developed the STEPS simulation code, which stands for stereographically projected cosmological simulations. Yes, I have to read this because I don't know its name. So the general idea is that to drop this translational invariance of simulations in favor of some kind of rotational invariance. And this STEPS code, it realizes that in actually a very funny way, because it is actually based on a very simple idea, which is stereographic projection, that was well known by ancient Greek philosophers already. And so this stereo projection is the method to map the surface of the sphere to the entire infinite plane, except for one single point in the pole, which is like marked with a Q in this figure, because it maps to infinity. But this method it can be generalized to higher dimensions, and this is exactly what STEPS does. It basically compactifies the 3D infinite universe into a 4D hypersphere. And due to the nature of the stereographic projection, the simulation in the real 3D space will have a gradually decreasing resolution as we move away from the center of the sphere. I do not want to go into details about this, but this approach where an infinite universe with a rotational symmetry is realized, it is much closer to physical reality than what was always done in cosmological simulations. This periodic force calculation with this in this cube with an arbitrary force calculation, cutoff distance, which are all just for the sake of numerical convenience. Okay, so now that we have a code that is capable of simulating a spherical infinite universe, it becomes trivial have to define some rotational axis, for example, the z-axis that I will show you in these figures. That's what I use for these figures. And if we have a rotation axis, we can just simply rotate this universe around it, just like we would rotate a ball in any other case. So we want to run the two types of simulations. One is with a forceless initial condition where the universe expands, but the particles are not moving relative to each other during the simulation. We just simply place down the particles in the initial conditions in a way that the sum of forces on them acting on them is zero. That's it. That's the forceless initial condition means. And then we want to run another type of simulation, which is a regular cosmological simulation where the large-scale structure formation of the universe is happening. What I'm showing you here in this presentation is the first type of simulations. And visually, neither of them will be different than any other cosmological simulations in general, except that this STEPS code produces these spherical simulations. So you won't see any effect of the rotation in these figures. What you actually can see, because these simulations are in non-comoving coordinates, what you can actually see is the expansion of the universe. So we started from this small little black blob of particles you can see on the left panel. And I zoomed in the center, in the middle panel. So that's how particles are distributed in the center and in the entire simulation. And on the right panel, you can see the final state of the simulation. The universe expanded. The zoom level of the left and right panel is the same. And that's basically the expansion of the universe. That's what you can see. So on this bottom panel, you can see something else. This is the displacement field of the simulation. And we're looking at particles from all the three different cardinal directions. So this is the XY plane, YZ plane, and XZ plane. And the displacement field is what its name suggests it is. We basically connect the initial and final positions of the particles with a vector, and the length of the vector is their displacement during the simulation, and that's what you can see here. And we usually plot this in comoving coordinates because we are not really care about the Hubble flow, the expansion of the universe, this radial expansion. We know that's there. We only care about the relative motion of particles relative to each other. And if we would plot the displacement field in the forceless simulations like this one, we would see nothing basically on these in the center and the right hand figure. the image would be filled with zero-length vectors by definition, because forceless initial conditions in co-moving coordinates, no movements of particles happen. Instead, it looks like this. So on the XY plane, you can beautifully see this rotation, basically, of the universe that we applied in around the z-axis. On the other hand, on the two other panels, you can see these. Well, usually in simulations, in normal cosmological simulations, these figures look like a fur of an animal. Actually, that's how they're supposed to look like. And it means that a large-scale structure formation is happening. In this type of simulation, it should not happen. It only means that our initial conditions are not entirely correct, but this effect is extremely small in that case. So I tested the final state with a halo finding algorithm, and although the particles move around a bit, just a bit, there's no really any structure or halo formed in the simulation. So it is still close to a forceless simulation, what we wanted to simulate. I'm just showing you this for transparency, that's all. So, okay, what I mentioned in the beginning is that we wanted to measure whether there is an observable effect of this rotation, or more like there is an observable difference in the expansion rate of the universe, because that's the theoretical prediction. And we can do this by measuring the scale factor of the universe, so the expansion of the universe in two orthogonal directions. One, we measure first this the scale factor, the expansion of the universe, first parallel to the axis of rotation in these two so-called spherical sectors. These are basically conical regions. You should basically visualize them as light cones. And everything that falls into these light cones, the particles, we take those particles and now we remember them. And then you can see these light cones. These are centered around the axis of rotation. So you can see them in the YZ and XZ plane going up and down in the simulation. And then we measure the scale factor orthogonal to the rotation axis in a so-called, well, equatorial bear. This shape does not have any name in geometry, at least I didn't find any name for it. But it's basically created by taking a spherical sector, like one of the above, for example, that red cone. We rotate it by 90 degrees orthogonal to the axis of rotation. And then we rotate this solid around this cone around the axis of rotation, creating a solid of revolution around this conical strange belt around the equator, centered around the equator. And this is the belt you can see on the bottom figure. And so we select both of these in a way that their volumes are equal. So both the volume of the equatorial belt and the sum of these two spherical cones are equal. And we calculate the scale factor for particles inside these regions. Okay. And okay. And on this slide, you can see the results of these simulations and the measurement in case of the lambda CDM cosmology. We compare the regular static simulation with the non-rotating simulation and simulations with various degrees of rotation. And on this result size, you can specifically show you the comparison between the non-rotating simulation and the simulation with the maximal possible angular velocity. On the x-axis, you can see the age of the universe in gigayears. I don't know the current age of the universe, but I think the last data point is at 30 billion, 700 million, I don't know what, something like that. So it is obvious that in a non-rotating simulation, nothing happens. So the scale factor is the same, the expansion of the universe is the same in all directions, both parallel to the rotational axis and both orthogonal to the rotational axis, besides some numerical errors. However, the rotational simulation or rotating simulations shows signs of a very strong anisotropy in these two directions. So strong in this case means that it is a 1 or 2% effect, which is actually pretty huge in today's precision cosmology, but this is not unusual to find these 1-2% effects when testing these funny models in like this one. So now, what are the implications of this simulation? So can this affect be observed in actual observations somehow in real measurements? This is not easy to answer because, well, cosmology is terrible. So there are a growing number of recent articles that claim that a directional dependence of the Hubble constant, so basically the expansion of the universe, can be observed in real data, but others say, based on very similar data, that no, there's absolutely no anisotropy, and then now you can decide who you want to believe. I do not and cannot want to answer this right now, since this is just a funny project we wanted to try, and its current state is just to explore this interesting phenomena that no one has ever done with cosmological simulations. But that's basically all what we wanted, and thank you for your attention. That's all I wanted to say.
Okay, time for questions. Opur?
Right. It shows that you claim here the rotation angular velocity. Is it today's value or the initial one you started?
No, so, yes, that's today's value. That's today's value.
How do you get this estimate?
That's what. So István somebody calculated that to not violate causality, basically, that's the fastest rotation the universe can have. I don't know about that calculations exactly, so that's, you should ask him about how he got this answer. But this is the maximal velocity the universe can rotate today. Of course, it loses rotation, so it slows down basically as it expands. It starts with a much higher rotation rate, but this is the maximum you can get to not violate causality.
Thank you. So how do we define the center of or axis of rotation of the universe?
That's a good question. Nobody knows, actually. So yes. So there is okay. It's really not easy to answer. So because we actually don't know, we just defined basically a sphere and said that this is the universe and there is an axis of rotation in a ball. Like there is more like a philosophical question how to define a rotational axis for the actual universe itself, because whether it's finite or infinite, and okay, you define an axis of rotation, but relative to what everything is rotating in the universe, this is not easy to answer, and currently no one has an answer for this. There are people who tried more, actually, I forgot the name of the philosopher whose original idea was this. Oh God, I forgot his name. I'm sorry. But yeah, this is very, very, have to say that we just defined it in this context as we could. That's it. So there's no real way to define it.
Okay, thank you.
Actually, on your figure, you can distinguish here because for the simulation, you choose an arbitrary axis to get it. But the last figure, where you have this asymmetry in the scale, it defines you the axis.
Yeah. So that's the idea that if there is a rotational axis or something like that in the real universe, it should introduce an anisotropy in something, either the microwave background or in supernova measurements, whatever, we don't know. But how, yes, we don't know how it actually works. So is it outside the universe maybe, and how do you define that, or is it inside the universe? It's really that's more like a philosophical question almost, not just a physical. So So that's why I'm having a hard time to answer, because yeah, everyone has a hard time to answer in the literature as well. But yes, it should define some kind of axis of rotation if it's a measurable quantity in real measurement.
Okay. Further questions or remarks? I would have question related to two things. That can you go back to the toroidal picture you had in the beginning? Yeah, somewhere here. So for the stereographic projection, you have a same periodic boundary. So this is the way how you move, that you have the periodic boundary condition, put the particles randomly and then move to the stereographic projection, or you have a stereographic projection and then you make a kind of flat distribution of the particles after doing the maps of the thing. So how is it made?
So in the original article of the
rats,
rats, they said that so there's currently no real methods to directly create a stereographic projection of particles, and I think they start from an actual cubical simulation, and then they map with some tricks to this stereographic projection. But that, yeah, I'm not sure about that part of the initial condition generation. Yeah, I know that it involves some tricks to make it work because there's no really known method. They had to invent something for that. But basically, that they start from some cubicle and then they map this stereographic projection to my best knowledge.
And one more, yeah, Tony, yeah.
Just a stupid question. If you have a rotating space, doesn't it show up in the rotation of galaxies in some ways?
I don't know actually. That well, it's really hard to say, where a rotation would show up. Yes, we talked about whether the rotation of galaxies would appear something like that. István Szapody said that he doesn't really know. I don't know. It could show up anywhere, actually.
Coriolis type of force, but the question, I mean, okay, the point one, I mean, it's not defined where you can see to a certain distance and you cannot know that what is beyond. Even there can be an axis of the rotation, but you cannot get it. Only just very tiny time frame after the burst of the universe. But the other issue is that everything has to be compatible with the lambda CDM model, which is the most accurate model of the universe as of today. So you can introduce rotations, but it shouldn't be appear as a direction if you do the measurements based on CBM and others. So below this threshold, you are free to do any with the theory. Above this threshold, of course, it's ruled out. So that's this kind of things of the problem.
Local
should show up, but if you choose a very low slow rotation, probably the Coriolis force is not so relevant. But this is the thing what we are doing with Balázs in an analytic model. So maybe we can calculate this also. Thanks for the question. You had this is the last question. Yeah, you don't want to ask. Okay. So then I have a very last question. So how much does it longer to run the zero rotation and the rotation on the machines, the same machine?
It's the same time, so there's no difference.
So
there's no difference between them. So
that's interesting.
Yes. Okay, STEPS is an interesting code because it's very novel and very different than any other types of simulations. So there's many things that maybe in regular simulations would be very different and harder to make and calculate and whatever. But STEPS, one of the main differences in STEPS that it uses much less particles and much less memory than any other type of cosmological simulation software. So it really has an advantage of calculating basically everything very fast, and there's no real overhead or time difference.
Okay, so let's thank Balázs again.
Yes.
And let me call Daniel Berini. I think most of you know very well because he was also one of the founder of the GPU laboratory long time ago, somewhere in the far galaxy. So Donnie will speak about the parallel image